The acoustic bubble. Thank you for coming. It's nice to see I think I know about 3/4 of the faces in the audience, so thank you all for supporting. This is a film of a drop of milk going into a cup of coffee. And the same white drop comes out as goes in. And so you can use this if you're still young enough to try and impress people at parties, and when they say, do you want milk in your coffee, you can say, yes, please, and then as that drop comes out, you go, no, and you can catch it again. It's a good party trick, unless you hit the cup. Now that makes the sound of the dripping tap, the plink, plink, plink that we're used to. But in fact, nothing that you saw in that film makes a sound that you hear. Where the sound of the dripping tap comes from is shown in this picture. So what I have here is a drop, water. It's in some air. It's above some water. This is the air-water interface here. And this is an underwater microphone called a hydrophone. And this is the signal from the hydrophone. And as I'm going to play this movie, and as it steps on, we'll see a vertical bar coming down here as it moves along. And this was taken from me by Doug, I think, Doug Off in one of yours. You can credit Doug for all the high-speed movies, you see. So I'm going to run this movie now, and this is the plink of the dripping tap, this noise here, and you're going to see when it occurs. So down comes the drop, makes a crater. Crater begins to close. And that little bubble makes all that sound. And none of this other stuff makes anything, pretty much. And the reason the bubble makes so much sound is it's just like a little underwater bell or a gong. It's a ball of gas surrounded by liquid. And the gas is stiff, it's squashy. If you squash it, it wants to resist you and bounce back. And the water is massive, water is heavy. If you have a belly flop, you'll know that. And so it combines stiffness, squashiness, with mass. The same as just about every weapon that was invented prior to sort of 1400. You know, it's a wobbly thing on a massive thing, doing, doing, doing. You know, a bendy thing with a heavy thing. And so they're good at coupling energy into doing work. And the bubble's a bit like underwater bells and gongs. A big bubble makes a no-note blonk, and a little bubble makes a high note plink. You know, you can imagine there's this diver, and he's blowing these blub blub blubs, and you know what sound they're going to make, the blub 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 noise, not the plink of a dripping tap, which is a small bubble high note. So you get the idea. So you could listen to the sound of a breaking wave and imagine every little note is like a singer in a choir who's been given one note to sing that relates to their size. Basses, deep note. And so by listening to the song made by that breaking wave, you know how many bubbles there were and what size they were. And so when this wave breaks like this, lovely little piece of footage here, not taken by Doug. And the wave breaks, traps some air, and that air is ringing. Here's a column of air breaking up, so it looks like that. And so with the sound of that, we can put that sound into a computer, and it'll tell us how many bubbles there are and what size they are. Now, you've got great computers in your heads, and you can do the same thing. So I'm going to play a recording of sound, and there's lots of little bubbles in there making a noise, but you know, you're not trained up with a computer program, but you'll be able to hear that big bubble at the end. Can you see that's, there it is? And this is a time frequency one. So right at the end, we're going to get a low frequency bubble, and you'll hear it. You hear? You did that processing that we asked the computers to do. Count the bubbles, say how many there are. So it's a pretty simple thing to do. So we look at the oceans this way, because we say, look, the oceans are really important for the greenhouse gas budget. There's about 1,000 million tons of atmospheric carbon every year goes from the atmosphere into the oceans and out again. It's a huge sink and source of this carbon. It's important where and when this happens, because it can affect hurricanes, it can affect warming of the atmosphere, it can affect the budget that we do of carbon in the atmosphere when we try and work out how much fossil fuel is safe to burn, things like that. So we can treat the ocean like a giant piano, and we can listen to all those notes being played when the waves break, and we work out how many bubbles are injected into the ocean. But that's only half the story, because what we want to know is how many dissolve, How much dissolution takes place? Because some of those bubbles just rise to the surface and release their gas. So to do that, you do a second technique. So you've listened to the wave break, like this, and that's like somebody playing the piano. Fine, you've heard the notes. Then you wait some time for some of those bubbles to dissolve, and then you send notes through the ocean. And that's a bit like going to a piano, pressing down on the sustaining pedal and shouting at it. Those strings will rattle back at you. And those bubbles are still in the ocean. Can you see? This is some ocean, atmosphere, ocean, and here's some bubbles, and they're just hanging around because they take a long time to dissolve, to rise to the surface. So these bubbles are hanging around like loads of little bells, and they're waiting for you to shout at them. So I can send sounds through the ocean, and they'll tell me how many bubbles are there. So you get the program. What you do is, the wave breaks and it traps bubbles, and we know how many bubbles and their sizes because they ring at us. Okay, then we wait a while, a minute or two, and then we send sound into the bubbles and we count them to see how much gas has dissolved. And we tell a computer how to do that. And again, you've got computers. So this is the sequence of pulses that go through the ocean before the bubbles are produced. And this is the sequence when there's bubbles there. You hear them echoing back at you like in a cathedral? I hope you can. So by that, we can then, by listening to the noise when waves break and then sending sound through the ocean, we can work out how much greenhouse gas is going into the ocean. Because bubbles, what you've just seen is bubbles strongly scattering sound that's projected at them in the top. Okay. Now it's not easy to do. Sounds easy. I got a couple of PhD students to do it, and here they are, standing on the equipment. Let me do it anyway. We had that equipment out there for a week, and they'd each spend about an hour with spanners tied onto their arms, and then they'd come in, and we had a porta cabin, and they'd slam the door of that porta cabin, and say, "Oh, bloody freezing to death," and the next one would go out. And I'd send them out in pairs. I wasn't, there was a risk assessment, of course. Send them in pairs. At the end of the week, a crane came to move this thing from the beach. And as it was lifted into the air, I looked at the door, and it was covered in bloody handprints because they'd been bleeding every time they came off the beach. Anyway, enough of that. So we move from that to a more professional thing by piggybacking on some huge work that was done by the guys at the Oceanography Centre. So they have the ship, Discovery, and they have this 11-metre-long spar buoy. So it's designed to be lowered off a ship, off Portugal there, sit in the water, and just the top sits out. And they had control of the top of it, and they had cameras looking down at the ocean, and they have these things called wave wires. And as a wave goes past like this, it gets higher and higher up the wire, like this, and tells you where the wave is. And we have acoustic sensors there, listening to the ocean and sending sounds through. And from that, we built together a picture of how the waves break and what the bubbles are doing. So these are some of the, we feed that into a computer model, blah, 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 always very nicely. And so this is a section of ocean. It's 15 meters deep. It's got 120 meters that way and 100 meters that way. And here are some bubbles just trapped as some waves break. And the bubbles are color-coded for their size. So small bubbles around here are color-coded blue, and big bubbles red. And when you think about it, big bubbles rise well under buoyancy. So you expect the red ones to cluster near the top, and the little ones, the blue ones, to go down deep. And as well, there's big circulation currents in the ocean, and they can kind of spread them out. And so if we look at the results, you can see here, there's, again, blue at the bottom, red and yellow at the top, as these clouds are formed. And from models like this, you can calculate how much atmospheric carbon dioxide is going into the ocean. So that was one acoustic bubbly sort of thing that we did. And you see at the end they form this beautiful V shape due to an effect called Lamier circulation. Right. Okay, so here's atmosphere, here's the ocean, and we've said, look, it's very interesting how much gas transfers from ocean to atmosphere and back again. Bubbles have a key role in the transfer of gases from the air to the sea. and between the seabed at the sea, because there's an awful lot of gas in the seabed. As our friends at the Oceanography Centre, Angus and John here, you know, are very expert in, you've got a lot of gas in the seabed, and it's important. It's important because methane is a very powerful greenhouse gas, and if that comes out of the seabed and enters the water and floats up to the surface and gets into the atmosphere, per molecule it's about 20 times more powerful than carbon dioxide as a greenhouse gas. And there's a lot of it. There's probably 2 or 3 times the amount of methane down there than there is of all the rest of traditional fossil fuels. There's an awful lot of it down there. And some people worry that, hey, if ever we get it's trapped in, a lot of it's trapped in the form of methane hydride. It's like an ice thing. And that will turn into the gas if ever the temperatures get a bit warmer. So some people are worried, well, suppose we get global warming, and that makes the oceans warmer, which makes some of this hydrate dissociate from being trapped in this form of ice into gas that gets in the atmosphere, which makes more global warming, blah, 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 end of civilization, that kind of thing. So it's important we know what's down there for fuel, for all sorts of methane reserves. It's also important because, again, just piggybacking on some excellent work down at the NOC, we're interested in looking at for carbon capture and storage facilities because we've got a lot of carbon in the atmosphere, and the idea is it's nice to get rid of it to stop, you know, end of civilization, that thing I was saying. So the idea is pumping it down into disused oil wells. So here's an oil well, a picture, and the idea is pump out the stuff, the oil, and put the gas back in. You've trapped it. But if ever it leaks out again, it'll be there as bubbles. So there's another reason why people are very interested in the role of bubbles in the transfer of gas between the seabed and the sea. Okay, so we drew this picture, and I think this is why I was invited to do this talk, because we wrote this paper, and it shows all the ways that you can monitor gas leaks from carbon storage and capture facilities like this, or from natural seabed, by using the yellow things, which are passive listening devices, those microphones. They might be towed behind a ship or an underwater vehicle, like this, or they might be sitting on the seabed. Or you might send out an active system, send out a sound pulse, just like that piano, shouting at the piano, and look for them. And they might be mounted on ship, or bottom-mounted sonar, or on the pipeline, things like that. And that was what I was asked to talk about. So enough of that, because I want to get onto the dolphins and the spaceships, really. So this is a sonograph, actually, of a methane seep from near Norway. And again, I've got to thank our friends at the NOC for launching this cruise, and my student Benoit, who was out there for a month on the ship, I think, taking things like this. And you can see, here you've got the seabed. This is, whoa, it moved prematurely. And here you've got these big plumes of gas coming out, and they're scattering back the sound that's sent at them by the sonar. So bubbles scatter the sound strongly that's projected at them. And the question is, because the bubbles scatter the sound, we can ask the questions, do whales sing in spirals, which is more interesting than methane seabed gas. I'm sorry, it is. I'm perverse. It's just... So here we go. So this is, I saw images like this, and I thought this is quite fun, because here you've got whales who are swimming in a spiral blowing bubbles, and they're doing it to catch food, fish, because it forms a kind of trap, and the fish can't get away, and the whales eat them. And it was always very vague about how why the fish don't leave the trap, because we know fish can swim through walls of bubbles. It's no surprise. So I thought, well, maybe there's an acoustical explanation. So here is a big spiral that's been built by these whales. And I worked out that, yeah, if you use a high enough frequency and the right kind of sound, then the sound would be trapped in this and form a thing. So I did say it has to be much higher than the sound frequencies than the sound used on the relaxation tapes. And it turns out it is. So I've got a recording of it here. I hope it isn't too loud, but have your hands ready. They do make an extremely loud call when they do it. So these are really high frequencies for a whale to produce, a big whale like this. And the idea was, the whale comes up and it sings, and because the bubbles scatter the sound that's projected off them, then the sound rays that they project tend to be trapped in this spiral horn-like shape. So it was a nice enough theory. And so you get all these things doing this, and you'd form a wall of sound, so that the prey, if they try and leave this net, those frequencies will shake their swim bladders, which is uncomfortable. You have to be a certain age to know if... So swim bladders, yeah, you get swim bladder resonance, but also it's subjectively loud. So we know, the idea was the whales to do that. So, of course, there's no proof, because no one's going to swim around with a microphone when they're about to come up and do things like this. So what we did is we took a model of the net and we launched rays into it as a whale would. There's the whale, and it's there. And you model what the sound does. You can see it bouncing around there, and you can see where the quiet zone is here. And that's where the whales tend to come up. So there's no direct proof. I don't know what whales are doing, but it's indirect enough to produce a great story. So whales do this thing in spirals. I don't know, but it's a good story. And it comes because of this issue that the bubbles scatter sound strongly that is projected at them. Now, I'm going to keep these two titles up here for the rest of the talk. And some of the stories are going to be about bubbles ringing like bells, and some about bubbles scattering the sound. And each story will be one or other of those. Right. Now then, whales. Big. I was going to say big and fat, but you can't say that about a whale. They're big, and they use low frequencies, and they do use it for communicating and perhaps for hunting. And we know that. And there's no complication with using sound for hunting. You know, you communicate, you shout, you get loud. Dolphins are much, much more interesting because they use sound for echolocation, which it's a crude analogy, but if that's the analogy of your vision, seeing what's out there, seeing the targets that are out there, they use sound for that. And bubbles give a hugely different issue for echolocation than it does for communication. Communication, I shout. If you don't hear, I shout louder. But when I use echolocation, when I use it for vision, I can be fooled by other things. I can misinterpret. So let's look at what acousticians do when they're interested in the area where the sea meets the beach, meets the air, because of course that's where a lot of military landings are. You know, if the troops jump off the troop carrier when it's not in this location, then something's gone badly wrong. So they're very interested in knowing about this location, particularly as mines and things are hidden here. So if you look at a lot of the papers, this is the model they like. It's a wedge-shaped piece of water. And we're going to look at like, well, no, I'm not going to forget that. So here we go. We've got sound reflects off the air-sea interface, and it also reflects off the interface between the sea and the sand. And it's easy to see why sound reflects off, sound in the sea reflects off the sand, because it's more dense. And, you know, if you shout at a mountain or a wall, it's more dense, it reflects the sound back at you. And in fact, and that's because there's a big density difference between the water and the sediment. But similarly, there's a big density difference between the sea and the air. So sound reflects off this. So these two things can look like mirrors because sound will bounce off them. So if your little old dolphin is here and starts echolocating, saying, what's happening, what's out there, this acts like a mirror, and this acts like a mirror. So the first thing he sees is reflections of himself, because if you have 1 minute mirror there, you see, if you look at that mirror, he would see that reflection. But because this mirror is there, it reflects that reflection to there, and so on. So when you look at a dolphin near the shore, it's like a hall of mirrors, something like this. It's a very confusing area. There's lots of spare targets out there. And in fact, it's a lot worse than that, because if I shine a light at a mirror, I did it in our bathroom, it looks like that. It's not very exciting. But if I put two mirrors next to each other, in a wedge shape, I see stuff like this. I see a series of fake targets, and I don't know which is the right one. And if you're a dolphin looking for a friend, or hunting a fish, or you're a Navy person looking for a mine, it's important, because suddenly one real target is turned into many false ones. It's actually much more difficult than that because of the bubbles. Because if you're this dolphin here, you're in an area like this. Now, for those who might know, this is the Persian Gulf. So you've got Iraq here. This is an important area, Tigris, Euphrates. And you see the water is all cruddy down here. That's because of mud and bubbles. This is the environment through which our aid ships and our military people had to contend with. It's no longer a clear area of water. It's not even a clear pair of mirrors. It's full of crud. It's not like a hall of mirrors. It's more like a hall of mirrors where the floor has suspended sediments. It's like going into this hall of mirrors with wedge-shaped mirrors, and somebody's put dry ice and mist in the room. And then the upper surface isn't flat, the upper mirror, because it's the sea surface and it bends like this. And occasionally generates bubbles, which make a lot of sound. So in fact, your upper surface is moving like this. It's a wobbly hall of mirrors with fog and occasional highlights, which are these given by these stars. So it's a very complicated environment for you to do something with. And I made a wobbly mirror just so you can see. There's a wobbly mirror. It's very confusing. Now you're trying to find one target in there. It's a very confusing environment. Okay. I'm as excited as you because I never know what's on the last slide. I've got such a... Here we go. So here we have a set of dolphins. And they're looking in this strange environment. Now, it's even stranger than you think, because the presence of bubbles can alter the sound speed by a factor of 2 over a second. And that means that for you, remember your visual, imagine you go into a universe where the speed of light changes by a factor of 2. You know, you'd be arriving before you set off from places. It'd be a very strange universe. And it changes every second, and that's because the waves are breaking and generate new bubbles every second. Now, if people went to such a universe, you know, science fiction film, it'd be really confusing about the only thing the human heroine could do is kind of have sex, because humans would still be able to do that, and they'd have the next generation and the next and the next, and after 10 million years, which is what dolphins have had breeding, you'd figure it out, particularly if you had big brains like dolphins do. So they've had 10 million years of breeding the next generation, and that breeds, and they've come up with some really good techniques of living in this very strange universe. And in fact, a lot of dolphin species just stay in this universe, they stay in this shallow water area. And I think it's because it's so hard for other species. They tend to be the little weak ones. They tend to be the small ones, not the big, powerful dolphins, it's the little ones. They say, you have the deep water. I'm going to use my brain and stay in the shallow water because it's too confusing. So the little weak dolphins tend to stay very close to shore. So here we have some dolphins. Now, you think it's hard enough for these dolphins because they're living in this strange near-shore environment where it's like a moving hall of mirrors. But some of them even blow bubbles specifically to hunt, like the whales do. And so we've got a little bit of movie here. It should work.
Thanks to the dolphins, the sardines have come within the diving range of the galaxy. Hundreds of white arrows shoot into the sea, leaving long trails of bubbles behind each dive. They're being released by the dolphins, working together in teams. They use the bubbles to corral the sardines into ever tighter groups. Sardines seldom cross the wall of bubbles and crowd closer together. Bubble netting in this way enables the dolphins to grab every last trapped sardine. Just when the feeding seems to be almost over, a brooder's whale.
Okay, so when I saw that film, I thought something's wrong. Because if you take a dolphin and you treat it as a sonar source, it's not nearly as good as the best man-made sonar source. It doesn't have the bandwidth, doesn't cover the frequency range, doesn't have the same power. It's okay, it's not great. But it has two things, really, that the human source doesn't. It's on a great platform. The dolphin can come at a target very, very fast, can look at it from many different angles, figure out what's going on. So that they can, for example, tell if a Coke can is filled with Coke or water. They can figure that out just by coming in at it. And the other thing you've got is huge brain. And so I thought, okay, well, we need to figure this out because the best man-made sonar couldn't see in there. They would interpret the bubbles as false targets, and the dolphin would spend all its time chasing bubbles and stuff. So either it it's blinding itself when it's hunting, which seems unlikely, when it's blowing these bubbles, or it's got a better sonar than we have, and it's either because it can move fast or because it's in its brain. So I thought, okay, let's go for the brain option. Now, you know, in the UK, we're British, we're not allowed to do experiments on dolphins. They all belong to the Queen. It's a Tower of London offence. So all you can do is armchair it. So sat in an armchair and think, what are they doing? So bubble scatter sonar strongly. How can the dolphin tell what is fish and what is bubble cloud? The best man-made sonar would not work here. So dolphins are either deliberately impairing their sonar when they make these bubble nets, or their sonar works in bubbles clouds where man-made sonar does not. So I designed a couple of sequences of pulses that they might use to see whether it worked. This is the second generation, because we did design one that worked, and it's apparent no dolphin uses it. So, you know, we came up with one. It does work. It's called TWIPS. For those of you who want to know what I'm talking about, nobody. It's lovely, but no dolphins seem to use it. I don't know. So I thought that's a shame. And it's based on the fact that when they send out pulses, one pulse is different from the next. It looks the same, but it's a version. Okay, let me explain. This is the second one. This is BIAPS. And this is, it stands for biased summation pulse sonar. I can't remember. And here the theory is that what dolphins do is they send out clicks. Like, they don't go click, 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 click. They go click, 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 click. They vary the amplitude. And that's what they do. And I think if you listen to dolphin recording, I should have played you one, it varies. You go click, 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 click. It varies the amplitudes. And it's just people just seeing this recording. It's just a coincidence, just laziness. But let's see if you can actually do something with that. Let's say the first click has amplitude 1, and the second click is just the same, but has amplitude 1/2. So it's half as big. Right, we can look at the scatter from the fish and the scatter from the bubble. Or if you're a Navy man, you say this is the scatter from the mine that you're interested in. This is the scatter from the bubble. So let's have a look. Now, let's take a bit of maths here. The dolphin sends out a 1 1/2, and they bounce out, they hit the bubbles and the fish, and then they come back, and the dolphin receives both pulses. Let's say it takes the second echo, multiplies it by 2, and adds it to the first echo. The scatter from the fish scatter exactly what hits them. A 1 followed by 1/2. So when you add them together, you get 1 plus 2 times 1/2, which is 1 plus 1, which is 2. So you get a strong signal from the fish. But scatter from the bubbles tend to scatter the square of the amplitude of the wave that hits them. And that's because they're what's called a nonlinear oscillator. When the bubble pulsates like a bell, it can get as large as it likes, but it can never collapse more than its radius because it disappears. So it's asymmetric. So it tends to scatter the square of the number. If you multiply the amplitude of the received echo, which is the square of what went out, by 2 and add to the first, you get 1 plus 2 times 1/2 squared. It's 1 1/2. Scatter from the bubbles, not so strong. Okay. What happens then if you subtract these same 2 echoes? This is the powerful one. So you take the echo from the second pulse that you receive, multiply it by 2 and subtract it from the first. And you get nothing from the fish. The target you're interested in goes away, becomes invisible. Whereas, because 1 minus 2 times 1/2 is 1 minus 1, which is 0. And the scatter from the bubbles is 1 squared minus 2 times 1/2 squared, which is 1/2. So they're still there. So the trick is to send out 2 pulses, click, click. And then mentally, take the second echo, multiply it by 2, add it to the first, and the stronger thing you think might possibly a fish. But you can do a double check by then keeping those pulses in your head, subtracting them, and if the thing you think is a real target, a fish, disappears, becomes invisible, you know it was, and you can attack it. Okay, so you send out click, click, you add the pulses mentally, you see the fish strong, bubbles weak, subtract it, see the, bubbles strong, fish weak, and they do send out these pulses. Unlike TWIPs, these are pulses that lots of dolphins give out all the time. So does it work? So, oh yeah, here's just an animation for you. Click, this is when you forgotten. When you do one of them, and you one of them. You see, and you find out mentally, you take, add, subtract, blah, 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 and you should be able to see what is the target and what isn't. So we did try it. Now this is a sonar picture, and this is, it says time, but it's distance because it's time of flight. And this image has a target in there. It's actually a metal disc and a load of bubbles, big load of bubbles. And when we add, we want to see the target. And when we subtract, we want the target to disappear and the bubbles to appear. And you can see it works. You know full well that's the thing to attack. So it seems to work. And we use this with actual dolphin pulses. You play dolphin pulses through an underwater loudspeaker, and it seems to work. But it's a curious thing, thinking that, well, here's these dolphins squaring and adding numbers and doing addition and subtraction. Not just a great big smile. And here they are. You see, they hang around in this water. What are they doing? Because a herd like that should see that, pod like that should see that pod and all those echoes. And any fish they're looking for, it's just become targets called clutter. Should see targets out there all over the place. Be unable to hunt and operate. Yet they do. They love this shallow water area. And I think it's certainly it's consistent with the pulses they send out, is this kind of squaring, adding and subtracting the squared numbers. It seems to work. Okay. And again, this would be very useful in this area of the Gulf because of all this crud around the shoreline. Because there were a lot of mines, to be honest, put out there. And I think they weren't all recovered, and they're still there. So as aid convoys come in, there could be a possibility. People use this area for recreational purposes. We really like to find these mines and get rid of them. But the best man-made sonar can't do it. And it's important. If we look at the Gulf War, these are 3 ships, the Samuel Roberts, the Princeton, the Tripoli. And I'm just going to tell you the financial cost. There was a loss of life as well, but I don't want to go into that. Big numbers, $96 million worth of damage. For mines that you can pick up off the internet, literally, you can buy them off the internet for $1,500. This is the Tripoli, huge hole in the side from an LUGM, which is pretty much a Second World War design. It's a very simple mine. Pick them from the internet, $1,500. So you have a big problem here in asymmetrical warfare, as you want. We have now a Gulf area that could be used for regenerating a region, but there are mines out there, and the best man-made sonar cannot see them. And that's why the Americans send out dolphins, because dolphins can find them. But we want to get dolphins out of that arena because it is hazardous. It is a very hazardous arena. Okay, now, underwater mines are an issue, but you don't hear about them too much on the news because this is the problem that really swamps them in today's warfare. It's a convoy in Afghanistan. We all know about IEDs. IEDs are very bad things. Improvised explosive devices, homemade bombs, hard to detect because they're quite simple. You can make them about as complicated as they get is having a mobile phone near them. And, of course, a lot of the roadsides in Afghanistan are full of clutter. Coke cans, bicycles, stuff like that, rocks. It's very hard to find an IED. Now, some circuits are to radar what bubbles are to sound. They will scatter the sound non-linearly. They scatter the square of the numbers. These are particularly circuits that we're interested in because they're in triggers of IEDs. And so now the equations that I put out for TWIPs and BIAPs and those, they don't care that it's sound. They'll work with anything. They'll work with MRIs. They'll work with radar. So the question is, can we take that scattering, that squaring and adding of numbers, and build a radar that finds IEDs? Because it works with dolphins. Okay, here we go. So this is a test that we've done. These are unpublished results. So we took, this is a dipole and diode, a trigger, part of a trigger circuit for a bomb. And this is a big old aluminium plate, so we don't want to see that too much because that's the kind of clutter that they bury gets accidentally buried. It's trash. This is a rusty old bolt. This will scatter a little bit like a trigger, but we hope much less strongly because rust does give some of the features of these trigger circuits. That's 3 mobile phones, just for fun. And this is the results when we scatter them. So this is the aluminium plate, this is the trigger, this is the clamp. These are the 3 mobile phones, and I've got them in 3 conditions: when they're off, when they're on, when they're turned off, and when they've got a fake SIM card in there, because that seemed like fun. Now, the point is, what I've plotted on the grey here is how much of the plus signal they give compared to how much minus. It's how non-linear they are. So anything that's grey, there's just the background greyness, is as much linear as it's non-linear. Gives as much squared as it does. It's halfway between a bubble and Anything white is nonlinear. It would be a bubble underwater, but here it's a circuit that's scattering the squares of the number. And anything that's darker than the background grey is inert, should be trash. And you can see this is what's happening. The aluminium plate is darker than background, it's trash. This thing we're very interested in. This is the trigger. And then rusty clamp, I said it would be a little bit like a circuit, but much weaker, and it is. And then the mobile phones in the three conditions, you can tell what conditioning that, I mean, that's another story. But the really interesting thing is this is a dB scale, and this goes from -3 to +3. And if I put on the actual numbers they scatter, this scatters at 28.6. It's saturated, this scale. To get as white as possible on this scale, you'd have to scatter at 3 dB. This scatters 100 times more powerfully. It's an incredibly powerful sensor for these triggers. It's log scale, and not everybody's familiar with log scales, but it's a good thing. Okay, now that was about bubble scattering sound that is projected at them. Now I'm going to do a bit about bubbles ring light bulbs when injected into liquids, which is this one. New topic, space. Of course, we've done the dolphins. We do the space, then we put dolphins in space. Oh, no, the Queen doesn't let me do that. I forgot. Yeah. All right, this is Titan. Some of you will be familiar with this. Titan is a big old moon out orbiting Saturn. And the nice thing about it is this purple haze, which is an atmosphere. And it's the only body, it's the only moon with a thick atmosphere. And the atmosphere is thicker than ours. At ground level, it's about 1.5 times as thick as our atmosphere. It's a good old juicy atmosphere. It's really thick. And the reason, even though this moon is only is smaller than a planet, the reason it hasn't boiled off is because it's very, very cold. And so it keeps this thick atmosphere. And it sits here on this planet, has done for a long time. And we haven't been able to see through this atmosphere. You can't see through it. Fly past because it's thick, full of smog. And it's full of smog because it's full of rich chemicals. And of course, NASA will say, possibly the chemicals of life, because that's what NASA always does. It always starts a mission by saying we might find life, and then it ends it by saying, but here are some pretty pictures. And that's what they do. And it's worked for many decades, and they hope it's a trick that will work for many decades to come. So they were saying, here we have is Titan. It's Saturn's largest moon. It's the lowest surface temperature of any world we've explored, 180 degrees below zero. And because it's so cold, Titan's got this smoggy atmosphere. It's mainly nitrogen, but it's got a lot of other stuff in that are poisonous and very cold. The smog is so thick we never saw the surface, but a few people sat there and looked at the chemistry of that place and thought, I think there's rain, there's a water cycle. Obviously not based on water, it's too cold for water, but based on ethane and methane, which are, methane gas. It comes out of cows. It's a gas. Here, it was in the seabed, we talked about earlier, but it's so cold that it forms a liquid, a water-like liquid on thing. So a few people thought this might be the only place in the world, the only place we've ever found where there's lakes, streams, beaches, other than this planet. I was asked, and I said, look, we've got a probe. Lots of probes have landed on Mars and broken. If you put a microphone on a probe, the microphone is cheap. It's wonderfully cheap as a planetary sensor. It uses up very little of the information band. So I heard that, Dr. Joseph. It uses very low information. You know how telephones are radios are far easier to use than video phones. It uses very little information. It's cheap, little power. They're rugged. And so I said, look, if we start putting microphones on our probes, then if this probe were to land on Titan with a splash, not a crunch, and everything else failed, we'd know this is the first time we'd discovered an ocean open to the atmosphere, and beaches, babbling brooks, all that stuff. And in fact, after 7 years' journey, as Huygens descended through the atmosphere, it photographed this kind of thing, which was a picture I was incredibly happy to see, because these are canyons made from flowing liquid. This is ravines on Titan. And of course, we now know that there are lakes made out of ethane and liquid, but this was a mystery we didn't know. So anyway, here we were. It was 2005, and in 2004, I said, look, it'd be nice to see a splashdown. And the BBC was putting out movies like this, animations showing Huygens, the probe, parachuting down through the atmosphere. And it was showing a splashdown, and I was thinking, yeah, but wouldn't it be great if we heard a splashdown? But then obviously the question is, would we recognize it? Because our brains have evolved on this planet with this planet's water. And we know what a splash sounds like because we've always heard splashes. But it's not the same as a splash in another world. It might be a skloop or gloop or some other language. So I thought, okay, I'll work out, with the help of Paul White, who I'll acknowledge on the last slide, but in very small writing. So let's run this movie, and then I'll play you the sound of an earth splashdown. So here it is. Here comes Huygens, splash, splash, and this is a splashdown on Earth. We built a model Huygens probe, mainly wok, I have to say, and we dropped it in the AB wood tank, and you heard the splash, and then you heard the gurgle as it filled with liquid, and then you heard the hiss of bubbles at the end. This is on Earth. Recognizable as a splash. So what would it sound like on Titan? So we take all that we know about how bubbles make sound, and we make that see how it would have sounded on Titan. Perfectly recognizable. So we would have recognized it. And then we can say, okay, well, would we, if it sat there on the surface, because it sat there on the surface about 3 hours looking over there, just looking there. And if there'd been a waterfall behind it, that would have been very sad. Not be great, but we wouldn't have known. But if they had a microphone and could recognize the sound of a waterfall, it would have been great. So I thought, well, let's do the sound of a waterfall. So this is a waterfall on Earth. Take all that information, transpose it to Titan. It's okay, a little odd, but it's workable. So, sound in space. I know I'm supposed to stick to methane, but here's a Mars thing. Why don't we send microphones into space? Well, it would be useful, because if you ask the rover to do something and you heard this, you think, yeah, it's opening a vein, that's fine. But if you heard it do this, you think, oh, something's gone wrong. I put those two veins, put these two veins, I should have tested opening these veins, but something like that. Okay. If you heard this, that would be nice. That's thunder on Mars. Now you don't get much sound on Mars because it's got a thin atmosphere. It's full of carbon dioxide. Carbon dioxide absorbs sound, and so it's mostly a silent planet. For the artists among you, C.S. Lewis wrote a book, Out of the Silent Planet, and it was actually the Martians were calling Earth a silent planet because we're so unspiritual. No spiritual radiation was coming from us. But in fact, Mars is the silent planet because there's so much carbon dioxide. It just eats up the sound. It's a very quiet planet. What microphones we have sent, as they've all sent to Mars, a silent world, I don't know. I would send to another planet, but more of that later. Okay, if we heard this, what would we think? It's just an old kettle. What else have we got? Now this is interesting. This is video footage. I mean, I make jokes about NASA, but they do a tremendous job. These are dust devils or whirlwinds on Mars, and so we thought, well, you know, Benoit, he's helped me with this. Raise a hand, Benoit. There you go. He helped me with this. We made the sound of what these would be. Doesn't travel far, but if it's close to it, you can pick up. Okay, what else have we got? This is an interesting one. See if you can think what this is. What you would think if you heard this sound from a planetary exploration probe. It's the sound of an iceberg. That's the sound icebergs make. Multipaths, you see. Further multipath, the closer the arrivals, higher the pitch, they make these jump. Choo, choo, choo. Why would be interested in icebergs? because of planets like this. This is Europa. This is Europa. It's a great big old moon. It's got an ice covering, and below it is an ocean. Enormous ocean. Our Arctic Ocean has ice over it and water underneath it. Our Arctic Ocean has a metre of ice, under which is 1 kilometre of water. This has 20 kilometres of ice under 100 kilometres of water. There's more water out there in the solar system. It's huge amounts of water. People think space exploration, what are we going to need? We're going to need food and water. So long as you get as far as Jupiter, you're not going to have a problem finding water. There's a whole host of water once you get beyond Jupiter. Now, this is interesting, and I can't remember what comes next. We might get. I think that's the end of. I'll give you another talk if you're interested in about the water here. But this is interesting because you've got liquid water so far out, which and it's liquid because Jupiter's got such a huge gravitational. It's crushing this thing all the time. It's like crushing a slushie. Keeps it liquid. And if you've got liquid water, that is actually a good inkling for life. It's a pretty it's pretty good. Anyway, here we go. Where does this go to next? So. I then got interested on the generation of sound and other planets. So we look at various instruments, because I did look at how various instruments sound on other planets, and I know you think this is frivolous, but as our colleagues in RIS know, the Research Council's refused to fund me, so I can do anything I like. So we look at instruments on other worlds. These are flutes. Now, this is an organ. Organs have some pipes that are like flutes, and we know that if you look at a pipe like this, then you can fit certain waveforms in them, and very simply, you can get various modes of waveform in them, and if you have a length of pipe D, and these modes are certain numbers of proportions of wavelength, and so you can get the frequency, and so you get the note of this thing. You know what I'm talking about. The longer the pipe, the lower the note. You know, if you hear the piccolo, it's very different from the bass flute. Long pipes, low notes, and that's because it takes such a long time in a long pipe for the sound to travel from one end to another. But if you go to another world where the sound speed in the atmosphere is very fast, it's very less time to travel from one end to another. So the pitch of the flute goes up, even though you haven't changed the pitch. So I looked at 4 worlds that have atmospheres: Earth, Titan, which we talked about earlier, Mars and Venus. And if you played a D on a flute on Earth, these are the notes that we give: F sharp, D sharp, and high F. If you were on Venus, well, that's all right. It's not that interesting, though, I have to admit. What is interesting is that organs, only half the pipes on an organ work like this. They work like flutes. The other half are called reed pipes. And they've got a little reed on the bottom, like a mouth organ, you know, like a mouth organ reed, buzzing up and down. And there, the frequency depends on the vibration of the reed. So, reed pipes. Here we go. We have a little reed at the bottom, and that wobbles up and down. And really, the length of the pipe is only secondary importance. Now, people have been building these instruments for years. And they know the note they're going to get because they get the stiffness of the spring and the mass of the bob on the end. And they put the two together and they get the frequency of the note. And it all depends. The heavier this mass, the lower the note. And you know that if I get something heavy on the end of a spring, it's going to boing, boing, and boing. If I put something like... Okay. But one thing that we ignore is this atmosphere. Because as this ball goes up and down, it's got to shove some atmosphere out the way. So there's the ball going up and down, and what you forget is the atmosphere that it shoves up and down. Here's atmosphere, go. Here you go, atmosphere moving up and down. Now on Venus, the atmosphere is like soup. It's really thick. So the atmosphere that you move out the way in order to move something is actually quite heavy. And so it's going to drop the notes of any vibrating reeds and such like. Why is this important? Well, you know, I wish I knew it was on the next slide, but I don't. You know, they have built sensors for Mars that are little vibrating plates, and they put them down on Mars and said, if ever any bacteria grow on this, they'll add weight to this sensor, and the pitch will go down, and we'll know there's life there. But of course, it's calibrated on Earth, different atmosphere, it's moving a heavy atmosphere. You didn't think. That's not really why I did it. I did it because I'm interested in the voice. So this is a human. It's got lungs, nose, mouth bit, and the vocal folds, or vocal cords they used to be. And when we speak, we wobble these vocal folds, and they wobble like this. And it's the wobbling of those. Every time these wobble, it gives you a pulse, like here and here. And the time between these pulses gives you the note that you're singing, the pitch. Ba, ba. I'm wobbling the ba, I'm wobbling them higher, faster, wobbling these things faster, the ba when I'm going lower. Okay. And so that gives me the old, whatchamacallit, the note that I'm singing, the pitch. But every time we pulse like that, here, sound waves bounce up and down this long tube. And they give these little echoes here. This is a bit like the reed organ pipe. You know, it's a vibrating thing in a column. Now, I like Venus for many reasons. And one is that the soupy atmosphere on Venus will slow down these vocal folds. They'll beat slowly, and you get a low note. So your voice will be low pitch on Venus. But Venus has a really high sound speed. So these echoes bounce, wham, wham, up to the top and back again. So you get very fast oscillations there. Now, if you hear these oscillations, these echoes coming very quickly, you think the windpipe was short, because it didn't take long to get back, because you're programmed to think in times of airspeed. So if you listen to someone on Venus, you're going to think they're a bass dwarf, bass smurf. I only say this because I have no idea what's coming up in the next slide. Okay, now why do we evolve this? Well, here's us evolving as cavemen, and you really want to know. You're used to pitch, you can hear pitch, blah, 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 you're used to that. You work by it. But we also are programmed to listen to this and hear clues. You may not be conscious of it, but whenever you hear someone's voice, you're interpreting how big they are. And you want to know, because if you hear a roar of this thing in the night and it's dark, you want to know whether this is a big thing that's going to hunt you and you need to stay in a cave, or whether it's a cute little thing that you might hunt and you can send a dopey guy to. You want to know the size of the thing from the roar in the night. And that's very important. And you've got all this computing power devoted to it. So, does it have impact? Well, I'm consulting on this film that Hollywood are making on The Last Days on Mars, and I've given some advice, and I don't know any of these. I know this guy, he was in X-Men Origins. He was the Sabretooth. It's big. Oh, don't know. Impact. This is a shot from behind the curtains at a fashion show, because there's actually going to be a fashion show that a young woman, a designer's doing. She's building some outfits for a fashion show this summer based on the sound in space. And so she's got spacemen and we talked, and she realizes that it's very hard to hear on Mars, so she's got this ear trumpet thing. So yeah, and thanks for going behind the curtain at the fashion show and photographing the models, Phil. But this was fun. I don't know if any of you saw this. This was the once a year the Dutch have a kind of quiz show, the annual quiz. It's for a lot of money if you get all 15 questions right. And and it's like Who Wants to Be a Millionaire or Weakest Link or something. And question 10 says, if you were to speak on Venus, what would your voice sound like? A dwarf with a quiet voice, dwarf with a high voice, all this stuff. You get these options. At this point, actually, I'll try to play you a bit because it was fun. Okay, so here we go. So they've asked the question, and the nice thing, you've got to admire the Dutch, they just spend 6 minutes explaining the physics to the contestants, isn't that? So you see he's got a voice, they've got some balls with springs on it, anyway, and if you listen, they acknowledge the university. Hang on, you missed it. Here we go.
Die heeft 2 regels ingezongen. Ja. En die opgestuurd naar de University of Southampton in Engeland. En daar heeft professor Layton door dit onderzoek hoopt de NASA ooit ook microfoons in te kunnen zetten bij onderzoek.
These contestants sit there going.
Nou, jij hebt een stukje gezongen. Laten we eerst eens even luisteren.
In de studio? Ja. Oké, nou maestro, geef maar muziek.
Liedje over Venus, hè, natuurlijk.
God is on a mountain top, burning like a silver flame. God is a beauty and love, Venus was her name. She's got it.
Okay. Anyway, they then sent us the sound files, and we gave her the voice she'd have on Venus.
Oké, kijk of je net zo mooi klinkt op Venus, maar dan moeten we even op het formaat van Lottie letten, want dat is lastig. We moeten eigenlijk een hele goede installatie hebben, want het zijn hele subtiele echo's die niet elk geluidssysteem.
See, he's talking about the echoes, he's doing his physics.
Laten we gaan luisteren naar Lottie op Venus.
God is on the mountain top. Burning like silver flame.
Okay, so you get the idea. So anyway, impact, where were we? Now, of course, you know, other people are saying, why are you doing this? And I can keep saying, well, if you won't ever fund me, you know, you get what you ask for. Rejected me 4 times this month, 4 times. Anyway, but this is a plane that they want to send to Titan one day, and of course they need to get the interaction between the atmosphere and the structure right if it's going to fly. This is a big old airship that they're talking about using on Titan, which would be fantastic. Again, you've got to get the interaction between the structure and the atmosphere right, and vibrations and something. But and, you know, people say, is that why you did it? No, it's not really why I did it, apart from for a bit of fun. A lot of the time when I was doing it was for this, because if you take the mouth and you take the windpipe and you write the equations for that, in order to do all this, and then you turn them on the head, you get a nozzle like this thing, which is chickpea can free, and it squirts water. So this is a project that I was working on with old Peter Birkin from chemistry, and we had Doug here, and it's for cleaning. So the principle is cold water goes in, cold water comes out, and it cleans. You don't have to heat your water, which takes a lot of energy in the home. You don't have to add much surfactant. We do this without adding cleaning fluids as well. You recycle the water. So basically, you save a ton on your energy bills. You can clean with cold water. You don't have to use much water, maybe a 20th of what you use in a pressure washer, and it cleans. So I'll give you some examples. So we'll play you now some soot on an old tile that's got a lot of soot on. What's going to happen is you're going to have cold water pump going through, and then have to count down 5, 4, 3, 2, 1. We'll just turn on the sound and play the sound down the stream of water. A kind of inverse of what we're doing when we're thinking about Venus's soupy atmosphere in the thing. So here we go. It will play. So it's water. It's not removing the soot. 5, 4, 3, 2, 1. Turn on the sound. Off it goes. We've got all sorts of examples like this, and this says "and finally," but it's not the end of the talk. That's just because Doug likes to add words in front of the. So and finally, this is lipstick. Now lipstick's designed to be very hard to get off, and so here's our little stream of water from this thing, and water doesn't remove lipstick, which is good for all those kissers out there. And then we turn on the sound, and off it comes. So we want one of these in every home and hospital. There's donations at the door. And so that was an impact from the sound in space work. Okay. So I'm closing up the talk pretty soon now. Impact, because there's been lots of talk about impact, which is what use is made of your work outside of academia? Because the government's very interested in that, as I know a lot of people in this room are interested. So sonar, yeah, we've developed a sonar. Yes, some sonar companies are interested in it. And it's nice, but it's really mostly my entertainment. Bubble detection is more impactful. We're doing work for oil companies, and this is the Oak Ridge National Laboratory. It's a $1.4 billion facility in the States, and here's us putting our bubble detectors on their Newton generator to solve a problem that they had. And to do with bubble detection. But really, the impact, I think, of the work is a topic I've never mentioned, which is the biomedical aspects of bubbles. So this is a good friend of mine, Gail Tahar, in the Institute of Cancer Research, and they're looking at using ultrasound and interacting with bubbles. We had a project for tumour, destruction of tumour, and here you can see an area of a liver, and here's an area that we just cooked with ultrasound, generated little bubbles in order to get rid of tumours. This is a device that we've now got that's been used in hospitals, and this is, if you have a kidney stone and you have it destroyed by shock waves, they fire a shock wave, 1 second, bam, 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 at your kidney stone to break it up. But they can't tell when it is or isn't broken up. So half the people have to return again because they're sent home and without the kidney stone breaking up. And half the stone probably broke up halfway through the treatment, and they kept treating them, which we know does lead to side effects. And so we have this device with colleagues at Guy's and St Thomas's Health Trust, and so that's been used on patients, looking at the sounds that bubbles make when this shock wave hits them in the stone. If we look more, this is a needle-free injector, and I think they've sold over 1 million of these now, and it's got federal improvement. And again, we looked at the bubbles in this in order to help the company develop this. And it's an injector without a needle, needle-free injector, and that's FDA approval now. But really, I think the biggest impact is to do with this. This is an old baby scan from the time when many of you were, from about 30 years, from many of you. No, it's an old one. And back in the 1980s, I took this photograph, which is a bubble being collapsed by a sound field very similar to the one that goes in to look at baby scans. And each point of light in that picture is a single photon. And what's happening is the bubble is collapsing, and the gas inside is getting hot. The sound field, the medical sound field is collapsing it, and it's causing the chemical reactions which give out light. So you're getting this effect here. And this is a kind of modern-day baby scan, and you can see far better quality because they've gone up in the frequency to get much finer resolution, but these higher frequencies are more strongly absorbed. So to get the same signal strength back, they have to use much more powerful machines. And over the years, the amplitude of the signal from baby scan has gone up and up and up inexorably. And really, it's driven by the clinicians want good pictures. The manufacturers want to sell machines, so they want to give these pictures. And what's standing in the way is a group really of, not only standing in the way, but just putting some hazard assessment on this. Engineers, physicists, biomedical engineers, who look at the effects that sound have on the developing fetus. And really there's two effects. One is the bubble activity and one is simply warming up the fetus. And so a group of us, it certainly wasn't led by me, a group of us in the 90s produced the guidelines, and I think every child born in the Western world who's had a baby scan, which is now most of them, since 1998, has been scanned under the regulatory guidelines that we put in place. So it's every child in the Western world today has had that scan of those guidelines, and I think that's the biggest impact that these bubble acoustics have had. Okay. That's the end. I will thank Peter Birkin, Doug Offin, Paul White. There were PhD students and others, but these are the three that I thank. And I thank you for attending and for your attention. Thank you very much.